Okay, so here then is a slightly more complicated energy kind of problem here. So this is a problem that has conservation of energy with energy of a spring. We're going to throw a spring into the problem and see what happens. I thought this was calculus-free physics. Can we not integrate? I thought this was calculus. Okay. Work on the, I don't know. This is calculus. Oh, you're just trying to piss me off. That's what it is. I've been trying to tell the whole world that 125 is calculus-based. I've been screaming it at every PAA I can possibly find. I just grab PAs. It's calculus-based. And it doesn't matter. People still think it's not calculus-based. Okay. And that's only the beginning. I can't even tell you about the other problems related to bad information about the intro physics series. Okay. What we got now is a mass sitting on a curved ramp. Now you're going to see the power of the energy approach. Okay? A mass on a curved ramp at height h on a frictionless surface, mu s equals 0, if you know what that means, aka frictionless, if you know what aka means. And then it's going to go up here to a spring. Right? And then we're going to say, what's it going to do? It's going to fall, it's going to slide, and it's going to, oh, look, it's already compressed it. It's going to compress the spring. So it's going to make it to here, to point C. So the two questions you could ask is, how fast is it going here? And then how much compressed here? How compressed here? Okay. So it's really not that much harder than the last problem. We're going to do basic, simple energy transformations. But, this will be the last one that we do that's just the basic idea. And then they'll get more weird. Okay, so first let's see, how fast is it going here? And you say, well, it's no longer a pendulum, so maybe it's somehow different. No, it's not different. It's the same. Okay? Let's make our lives easy and say this is y equals 0. And this is also where the gravitational potential energy equals 0. Right? That way we don't have to think about deltas. Okay? And then I'm calling this state A, and this is point B and point C. So let's first do, the first question was A to B. Mathematically, it's just like what we did before. But let's do it, just to make it slightly different, let's do it with this formula. Delta K plus delta U equals 0. Right? So that's kind of like the process formula, not the two-state formula. We're not thinking of this as the initial state and the final state. What about the process of going through these things? It's really the same thing, just maybe one would click with you more than the other. Okay? So what is delta K? Let's see. Delta K is K final minus K initial. What is K final? I don't know how fast it's going. That's what you're looking for. Okay, right. So 1/2 mv final squared is K final. What was K initial? It was released. Always means released from rest. Minus 0. So there's your delta K, that process. And now, what is U final? What is the final gravitational potential energy? 0. Right? And what is U initial is minus mgh. Right? Got to remember that minus there. It's final minus initial equals 0. Okay? So you look at that and you say, oh, this is just like that other problem. 1/2 mv final squared equals mgh. V final is the square root of 2gh. Okay? So just like the pendulum, same answer. Which that tells you a few things. One, it tells you, yes, you can use this. This really is the same as what we did before. Before we had E mechanical initial equals E mechanical final. This is the same thing rearranged. And it worked. The other thing it tells you is, it doesn't really seem to matter how this mass got from here to here, does it? Right? It could hang on a rope from a ceiling 10 meters in the air, or it could slide on a frictionless track. It doesn't matter. So that's what energy problems are for. You don't have to do the details. This could be shaped like this. It's the shock wave in Dallas in the 80s. Oh, I was too scared. I just bought the t-shirt. Right? It could go like that and go all the way down. It would still be at the same speed. It doesn't matter all the complicated forces it felt as it went through. All that matters is the initial and the final. Okay? That's what energy problems are good for. So if you're doing the final exam and you say, I don't know what the trajectory of that is, that's weird. It's probably an energy problem. Okay? how do you do this with friction? That's Tuesday. Right? So we'll add the friction Tuesday. Let's go from B to C. All right? So the question next is, how much is the spring compressed? So we could go from B to C. We could even do it from A to C. It's not going to matter, right? But let's do it from B to C. And I don't remember what I did in my notes. It doesn't matter. I think I can do this off the top of my head. I know I probably can't. Okay. Let's do this one by saying initial kinetic plus initial potential equals final kinetic plus final potential. Right? Let's just set that up and do it again here. Okay. So you have lots of paper. I don't. Okay. Okay. So in this state, what is the initial kinetic? 1/2 mvf squared, square root of 2gh squared. I'll even write it all out. There you go. For those that that like intermediate steps. What is the initial gravitational, this is now spring potential. So keep in mind we're going to spring now. Spring initial and spring final. Sorry, that's potential energy spring final. So the initial energy when we're in state B of the mass spring system is 0. Right? It's not compressed. I'll even write it out. Plus 1/2 k0 squared. Right? That's 0. And that must equal the final kinetic energy of the mass once it's compressed the spring, which is what? 0. Whenever I do this, you know the answer is 0. Which is what? 0, yeah. Because when it compresses a spring, that's when it stops. It's like a turning point, is what we call it in physics. 1/2 m0 squared plus 1/2 k. I don't know how much the spring was compressed. That's the answer, right? That's what you're looking for. Delta x, how much you compress the spring. Right? So these are equal. Right? And these I was writing for funsies. Those are 0. And this turns into mgh. Right? 1/2 m, square that to 1/2 mgh. So you get mgh equals 1/2 k delta x squared. So you see, we could have done it from here. We could have just said this mgh equals this 1/2 kx squared. And then it's just algebra E. It's 2 mgh over k, the square root. Right? So if you just want the final answer in your notes there, you could do it. I know you could do it. It's 2 mgh over k is what you get. Right? Okay, so this is another case of a simple problem. I mean, none of this is simple, but an elementary problem compared to homework problems. And if you just look at this and you say, well, I know, it's mgh, I put some here and I put some here, and you know what to do, then do it that way. Right? It was just mgh equals 1/2 mv squared. Mgh equals 1/2 kx squared. So you're fine to do it that way. But if you don't know what to do, you can use these formulas, and you can always get it right. Okay? All right. As long as you know what you're looking for.